Here is a number nobody in the consumer press is talking about. On some advanced AI accelerator chips, testing a single die after it comes back from TSMC costs more than the slice of silicon wafer it was cut from. $15 to $25 per die in test cost alone. On a 3-nanometer accelerator that costs around $8 to $12 in wafer cost per die. Test cost has crossed wafer cost, and it is climbing faster than wafer cost is shrinking. Every advanced chip that ships in 2027 has a hidden tester tax baked into it that the design press almost never mentions. The reason is geometric. 3-nanometer transistors are smaller, but the number of internal flip-flops on an accelerator just keeps growing. And every single one has to be exercised by a machine that costs millions of dollars and lives in a fab somewhere. The wafer keeps shrinking on cost. The test bill keeps growing. This is what design for test, or DFT, actually does. It is the engineering discipline that decides how big that hidden tax is. Get the DFT wrong, and the chip is either uneconomic to ship in volume, or it ships with bugs the customer will find in the field 18 months later. Get it right, and a billion-dollar product line works. This is the job, what it really looks like in 2027, and which two layers of the supply chain quietly profit the most from every AI chip that gets tested. The design for test engineer, the DFT engineer, is the person who adds the structures to the chip that let a tester machine prove the chip works. Not by running real software on it, by driving and observing every single flip-flop and every memory cell through a small set of dedicated pins in seconds across millions of dies at a unit cost the program manager will sign for. On a modern AI accelerator with several 100 million flip-flops and tens of megabytes of on-dice RAM, that is a hard engineering problem dressed up as an accounting problem. 4 walls define the role. Wall 1, scan chain insertion, turning every register into something the tester can poke. Wall 2, scan compression, shrinking the test pattern so the tester finishes in time. Wall 3, automatic test pattern generation, achieving the coverage target the customer's quality team demands. Wall 4, built-in self-test and customer-facing diagnostics, the silicon the customer will rely on for the next decade to root cause field failures. Each one is a place AI tools can help, but cannot finish the job. Walk through them. Wall 1 is scan chain insertion. The DFT engineer takes every flip-flop in the design, several 100 million of them on a modern AI accelerator, and wires them together into chains that the tester can shift values through. Like a long string of beads, where each bead is a state element the tester can both write and read. The number of chains and the length of each chain decides the test time directly. 2,000 chains of 100,000 flops each means 100,000 tester clock cycles per test pattern. Half the chains, double the test time, half the silicon area cost of the test infrastructure. The Synopsys TestMax compiler can generate the chain partitioning automatically. What it cannot do is decide whether this specific product line is willing to add 0.3% of die area to save 1 cent of tester time per chip, or vice versa, given that the customer is shipping 10 million units a year, and their procurement contract has a hard ceiling on cost per die. That is a 4-way conversation between the DFT engineer, the program manager, the customer's product team, and the foundry. The compiler runs after the conversation finishes, not before. Wall 2 is scan compression. The uncompressed test pattern for a modern accelerator is in the hundreds of gigabytes. The tester memory holds maybe a few gigabytes per channel. Without compression, the test pattern does not fit on the tester at all. Compression ratios of 100 to 1,000 times are routine. Synopsys TestMax compression and Cadence Modus generate the compressed pattern set automatically. The DFT engineer's job is to decide what gets compressed away because compression is lossy in a specific sense. It collapses test stimuli that share common signatures. Most of the time, the collapsed stimuli were redundant anyway. Sometimes the collapse hides a transition delay fault on a low toggle net that would have been caught by the uncompressed version. A higher compression ratio means a shorter test time, which means lower test cost per die. A lower compression ratio means higher coverage of subtle delay faults, which means fewer parts shipped with marginal timing that the customer will see as intermittent failures 18 months into the product lifecycle. The DFT engineer picks the ratio. The customer's quality target document gets cited. The chosen ratio gets justified in writing. Nobody at the compiler vendor signs that document. Wall 3 is automatic test pattern generation, ATPG, achieving the coverage target. Stuck-at coverage of 99.5%, transition fault coverage of 98%, path delay coverage of 90% for critical timing pass. The numbers in the customer contract. The Synopsys TestMax ATPG engine generates the patterns. On a typical AI accelerator, this takes a few hours of EDA compute and produces a coverage report. Usually, the first run gets 95 to 97% of the target. The DFT engineer reads the report. The remaining few percent are always the hard cases. Buses that go through 3 pipeline stages and an arbiter where the tester cannot easily construct the input combination. Custom analog interfaces where digital ATPG does not apply. Fault classes the ATPG engine simply does not have models for. 3 options each time. Write a handcrafted test pattern, which takes a day. Negotiate with the customer to reduce the coverage target, which takes a week and burns trust. Add design for test hardware in the next revision of the chip, which is a future tape-out problem. The DFT engineer triages, picks the path, and tells the program manager which one absorbed the schedule cost. Then ships. Wall 4 is built-in self-test and customer diagnostics. Built-in self-test, BIST, is the test logic that runs on the chip itself, without a tester, for things a tester cannot easily reach. Embedded SRAM and HBM stacks especially. Modern AI accelerators carry tens of megabytes of SRAM and several gigabytes of HBM. The BIST controller walks the memories at boot time, finds defective cells, and reroutes them to redundant rows and columns. A few cells per million repaired in place instead of throwing the entire die away. That repair is the difference between 50% and 90% yield on a new node. But the more important Wall 4 decision is about what comes after the chip ships. The DFT engineer designs the diagnostic registers, the JTAG interface, the error capture logic, the field failure traceback structures that the customer's hardware reliability team will use for the next decade. Every time a returned unit comes back from a hyperscaler customer with an intermittent failure at 3 in the morning in a data center somewhere, the DFT engineer's decisions years earlier decide whether the failure can be root cause to a specific transistor, or whether the field team just shrugs and blames cosmic rays and ships a replacement. That is a customer-facing decision wearing DFT clothes. A model running ATPG does not have a customer relationship. The DFT engineer does. So why is testing so expensive? And which companies actually profit from every advanced AI chip that gets tested in 2027? 3 reasons the cost stays high, and a 2-layer winner that takes the upside. Reason 1. Per die test time is the spec. The customer contract says test cost per die must be under $15, or under 5 seconds of tester time, or both. That number is negotiated months before the design is frozen. It is not a search problem for an AI tool to optimize. It is a contract problem the DFT engineer holds in their head while making every other decision. Reason 2. Cross-domain context again. Silicon area cost, tester time cost, customer quality target, foundry yield ramp curve, field failure return rate. The DFT engineer is the only person who holds all 5 in working memory. Reason 3. Customer-facing decisions persist for the product lifetime. The diagnostic registers the DFT engineer picks today will still be the way customers root cause failures 10 years from now, after this engineer has moved to the next program. AI tools do not carry that responsibility. So who profits? 2 layers. Layer 1 is hardware. The automatic test equipment duopoly, Teradyne and Advantest. Every advanced chip is tested on one or the other. Teradyne owns most of the AI accelerator and HBM test market with the UltraFlex platform. Advantest owns most of the SoC test market with the V9 3000. Each machine is between $1 and $5 million, and a single fab needs hundreds. As AI volume ramps, tester demand ramps. Layer 2 is software. Synopsys, TestMax. The DFT compiler that owns the AI accelerator design space. Cadence and Siemens have credible offerings, but Synopsys took the high end. The TestMax license per seat scales directly with the design size. The chip company pays both layers. The DFT engineer is the integrator who makes both vendors useful. That is design for test, the discipline that decides whether a chip can ship in volume and whether the customer can debug it 10 years later in the field. Real Silicon Jobs is the new series on the actual engineering work that AI is still nowhere near doing on its own. Subscribe to see the rest of the roles that ship silicon. Next episode goes inside the package engineer, the person who decides whether the thermal budget on a 500-watt accelerator actually works in a real server rack. Watch the numbers.